Assalamualaikum everyone. This episode is a revised excerpt of a past upload on the nuclear activity of cobalt-60 isotope used in the treatment of certain types of cancer. So stick around till the end of this video. Watch and learn. The question is, radioactive isotopes used in cancer therapy have a shelf life, like pharmaceuticals used in chemotherapy. Just after it has been manufactured in a nuclear reactor, the activity of a sample of cobalt-60 is 5,000 curie. When its activity falls below 3,500 curie, it is considered too weak a source to use in treatment. You work in the radiology department of a large hospital. One of these cobalt-60 sources in your inventory was manufactured on June 26, 2019. It is now October 6, 2023. Question is the source still usable? The half-life of cobalt-60 is 5.271 years. If we take the value of the reciprocal, the number of nuclei undergoing nuclear decay per second, we are referring to the radioactivity denoted here by Ace of Knot. In this problem, the activity of the isotope cobalt-60 is given as 5,000 curie, or that is 5.00 raised to the third power curie in three significant figures. The date of manufacture of the source of cobalt-60 used was June 26, 2019. So the length of time for this isotope to have started decaying as of today, October 6, 2023, is T equals 4 times 365.25 days. So that's 1,461 plus 102 days for a total of 1,563 days. We are also given the half-life of cobalt-60 equal to 5.271 years, or when converted to seconds, that is equal to 1.663 raised to the 8th power seconds. And our target variable is to find the activity capital A at time t equals 1,563 days. If the value of the final activity is still greater than 3,500 curie, then the source of the cobalt-60 isotope would still be usable. The nuclear transmutation in bold here is shown in this equation. All right, so cobalt-60 decays to the isotope nickel 60, all right, by emitting beta minus, that is represented here by an electron, and an electron antineutrino, all right? So the decay is initially to a nuclear excited state of the isotope nickel 60, from which it emits either one or two gamma ray photons to reach the ground state of the nickel isotope. The initial activity of 5,000 Curie, all right, is also equal or equivalent to 1.85 times 10 to the 14th becquerel, right? Becquerel is the SI unit for radioactivity, all right? So we obtain this by just multiplying 5,000 Curie by the conversion factor, which is in 1 Curie, we have 3.70 raised to the 10th power becquerel. We need also to find the decay constant denoted by lambda, which is simply equal to the natural log of the number 2, and that is equal to 0.693, all right, to be divided by the half-life, all right, the half-life which is uh, earlier determined or given in terms of seconds, all right. We have here lambda equals 0.693 divided by 1.663 raised to the power 10 to the 8 seconds. And doing our math, we will get the value of the decay constant lambda equal to 4.17 raised to the negative 9 power per second. Moving on to our computations, we convert the elapsed time of 1,563 days to seconds by just multiplying it by 86,400 seconds per day. So we get this time elapsed equal to 1.35 raised to the 8th power seconds. So we can now proceed, okay, in calculating the activity capital A using this formula. All right, the activity capital A is just equal to the initial activity A naught multiplied by Euler's number raised to the negative power lambda times the time t. All right. So substituting our given values, we have for A naught 1.85 times 10 to the 14th becquerel, and Euler's number is 2.718, all right, raised to the power negative 4.17 times 10 to the negative 9 per second, which is the value of the decay constant lambda. That's to be multiplied by the time elapsed, 1.35 times 10 to the 8th power seconds. All right? So when we simplify this using our scientific calculator, all right, this becomes 1.85 times 10 to the 14 becquerel multiplied by Euler's number, whose exponent we have just simplified to negative 5.63 times 10 to the negative 1. All right? The unit second has been cancelled. And further simplification of this will give us 1.85 times 10 to the 14th becquerel times the result of getting the value of 2.718 Euler's number raised to the negative power 5.63 times 10 to the negative 1. We get 0.569. All right. So when this is multiplied to A naught, all right, our value for the final activity, capital A, will be 1.05 raised to the 14th power becquerel, which, as expected, okay, is lower than the initial activity A naught, 1.85 raised to the 14th becquerel. And what does this mean? 1.05 raised to the 14th becquerel also means that there are 1.85 or 1.05 times 10 to the 14th number of cobalt-60 isotopes transmuting, all right, or decaying into the isotope nickel-60. That is in 1 second. All right? That is the meaning of our calculated activity, capital A. Our calculated value for the activity A is in becquerel. So, converting it back to Curie, we get A 1.05 raised to the 14th power becquerel is also equal to 2,840 curie. Now, in the formula for activity A being equal to A naught times the Euler's number raised to the power lambda times t, we can in fact isolate, all right, the time t and come up with an equation such as this. T is equal to the natural log of A over A naught divided by negative lambda. All right. So we will use this equation to calculate for the time t using the value of the activity that we have here, 2,840 curie. That is, t is equal to the natural log of A, which is 2,840 curie, divided by A naught, the original activity of 5,000 curie. All right? And then that will be divided by negative lambda, or negative 4.17 raised to the negative 9 power per second. All right? So doing our math, we will get the value for the time t, all right, equal to 1.35 raised to the 8 power seconds, which jives with our earlier calculation for the time elapsed t. All right? So, we just verified the computed value for our activity A. All right. So we can already make our conclusion as our final answer to the question. That is, the source of cobalt 60, okay, in this problem is no longer usable since apparently the calculated value for the activity capital A, which is 2,840 curie, is less than or lower than the critical value of 3,500 curie. Right? It looks like the time elapsed between the date of manufacture of the cobalt 60 source to the date when it is to be used. All right? 1.35 raised to the 8th power seconds, or that is a little more than 4 years. All right? That is pretty close to the half-life of cobalt 60, which is 5.271 years. So indeed, the radioactive isotopes used for cancer therapy in this scenario is already beyond its what we call shelf life and is no longer effective. So that's all about all. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.